Welcome. In this general chemistry tutorial, we'll look at calculating buffer pH using the Henderson-Hasselbalch equation. A buffer is prepared from 32.0 milliliters of 0.050 molar HF and 28.0 milliliters of 0.10 molar NaF, and we're given the Ka of HF. What is the pH of this buffer? Let's start by looking at the Henderson-Hasselbalch equation. It reads pH is equal to pKa plus log of concentration of A minus, that's the conjugate base, over concentration of HA, which is the weak acid. It's a special note that we can use either the molar concentrations or moles or even millimoles of A minus and HA, because it's the ratio of conjugate base to weak acid. Moles and millimoles can be used in place of molarity. So let's calculate millimoles of each HF and F minus. We calculate millimoles by multiplying the volume in milliliters times the molarity. For HF, we get 1.6 millimoles of HF. For F minus, we get 2.8 millimoles. Calculating the pKa, take the negative log of the Ka. So negative log of 7.2 times 10 to the minus 4, which is equal to 3.14. Placing these numbers into the Henderson-Hasselbalch equation, we find the pH of this buffer is 3.38. If we were to calculate the molarity of HF and F minus, we do that by calculating the concentration using the dilution equation, M1V1 equals M2V2. If we use those concentrations in the log term, it still gives us the pH of 3.38. Let's use that same buffer and now find the pH after adding 10 milliliters of 0.11 molar HCl. The reaction that is occurring is that the acid, as hydronium, will react with the conjugate base, fluoride. We need to look at how many millimoles we have of each before it reacts, and then how much is left after it reacts. So we already calculated millimoles of F minus and HF. Calculating millimoles of hydronium, we find 1.1. That comes from 10 milliliters times the 0.11 molar. So the amount of added acid as H3O plus will completely react to give us 0 left of H3O plus. We subtract the 1.1 from F minus, which gives us 1.7 millimoles of F minus after it reacts, because it's a 1-to-1 ratio. We also find that we add 1.1 millimoles of HF. So 1.6 plus 1.1 gives us 2.7 millimoles of HF. We then use those numbers in our Henderson-Hasselbalch equation and find the pH is 2.94. So when we add added acid to our buffer, the pH decreases slightly. Again, looking at that same buffer, but now let's add 15 milliliters of 0.10 molar sodium hydroxide. The reaction with added base is going to occur with the weak acid. When those two react, we produce the conjugate base F-. Again, we'll calculate the millimoles before it reacts and after it reacts. We still have 1.6 millimoles from our original buffer of HF. We have 2.8 millimoles of F-, and we solved for the millimoles of hydroxide by multiplying 15 milliliters times the 0.1 molar. Again, it's a 1-to-1 ratio, so the millimoles of hydroxide, the 1.5 millimoles of hydroxide reacts with 1.5 millimoles of HF, which leaves us with 0.1 millimoles of HF, 0 moles of hydroxide, and now we've added 1.5 millimoles to F-. Using the millimoles of F- and HF in the log term of the Henderson-Hasselbalch equation, we see that the pH is now 4.77 with this added base.